Programmable array logic. In short form, it's also called as PAL. We already saw PLA. In the PLA, we was having the programmable AND gate and programmable OR gate. Whereas in case of programmable array logic, we have only programmable AND gate and fixed OR gate. So this is the difference between PAL and PLA. Now, first we will see how to solve the numerical based on PAL. For that, we have to follow 5 steps. First step will draw the truth table. If the numerical is based on certain statement, so first we have to draw the truth table. If they provide us direct truth table, then that will be the first step. Second step is finding the minimal SOP form, minimal sum of product form of outputs. In the third step, we need to find out the number of input buffers required. Input buffer required. In the fourth step, we need to find out the number of AND gate, that are the programmable AND gate. And in the fifth step, we need to find out the number of OR gate. Here, the number of OR gates are fixed, whereas the AND gates are programmable. This is the only difference if you consider PLA and PAL. Now, we start with some numerical. For example, we get some numerical value like we have X in terms of A, B, C, and the summation M is given by 2, 3, 5, and 7. And we have the Y is equals to A, B, C, and the summation value is given as 0, 1, and 5. And this is the third output, that is Z. It's also in ABC terms, and it is given by the SOP form of 0, 2, 3, and 5. So how to start such questions? Here, as you can see, we have ABC as the inputs. So I'm writing here A, B, C are my input, X, Y, and Z are my output. As we are considering 3 input variables, total possible combinations will be 8, 0, 0. So I am writing all the 8 possible combination here, 1, 1, 1, 1. Similarly, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, and 0, 1. As the min term that we are having, the values are 0, 1, 2, 3, 4, 5, 6, 7. So wherever the X is available, like 2, 3, 5, 7. So for this value, 2, so before that is 0, 2, 3, then 3 is 1, then 4 is 0, 5 is 1, 6 is 0, and 7 is 1. Similarly, if you see Y is 1 for 0, so 1, 1, then 3, 2, 3, 4 are 0, 5 is 1, and 6 and 7 is also 0. If you consider Z, we have 0, 2, 3, 5. So 0 will be 1. Next is 1, so it's 0. 2 is 1, 3 is 1, 4 is 0, 5 is 1, and 6 is 0, 7 is 0. So this is the first step where we have drawn the truth table for these expressions. Now we have to find out the expression. How we can find out? By using the K-map. So here I'm drawing the K-map for finding the minimal SOP form. So second step is minimal SOP form. So minimal SOP for X will be having how many input variables? 3 input variables. So I am taking this side A, this side I'm taking BC. So this is 0, this is 1. And as you know, K-map is using the gray code. So 0, 1, 1, 1, and 1, 0. Now, as it's available at 2357, right? It's available at 2357. For that, I will write down here. This is 2, 3, and this is 5, and this is 7, right? So we can make a group here. One group I can make it like this, another group I can make it like this in the K map. So this will give you A bar B plus second, this one will give you AC. So this is the expression of X. This is the first part of the second step. Now we will find out the expression for Y. For Y also we have to draw the K map like this only. So here also I'm drawing the K map for Y. As we are having the three variable, this side I'm taking A, this side time I'm taking BC. So 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And for Y we have 0, 1, 5. So for 0, this is 0, this is 1, and this is 5. So again, we can make a group, one group like this and another group like this. So we can write down the expression here, that is A bar, B bar plus B bar C. So this is the expression for Y. This is A bar and this is B bar plus C, the B bar C. So this is the expression of Y. Now we will find out the expression for Z. So for Z also we have to make the K map. It's also a three variable K map. This side I'm taking 0, this time 1 because it's following the gray code. So 0, 1, 3, and 2. Now we have to see which variable, which terms was there, 0, 2, 3, 5. So 0, then 2, then 3, and this is 5. Okay. So now here also we have to make the group. One group will be like this. Another group we can make it like this. And third is not a group, it's a single individual term. So now we are writing the expression. We will get A bar B plus A bar C. And for this individual term, I will get A B bar C. So these are the expressions that we got for step number 2. This is the expression for Z, and that was the expression for Y. Now we have to see the third step. In the third step, we have to find out the number of input buffer required. So in third step, that is the number of input buffer required. It is always equals to the number of input. And in our case, we have A, B, C as the three inputs. So three input that are A, B, C as our three input buffers. Now fourth step is to find out the number. Fourth step is to find out the number of programmable AND gate. Number of programmable AND gate. So for that, we have to write down all the expressions that we got in the step number 2. So as we calculated the minimal SOP form of X as A bar B plus AC. Similarly, we calculated Y is equals to A bar B bar plus B bar C. Similarly, Z was A bar B plus A bar C plus A B bar C. Now, how to calculate the programmable AND gate is very important. Here, we have to check the number of terms, number of min terms present in every expression. So here in X, we have one term and two terms. So in bracket, I am writing 2. In Y, we have one term, two terms. So I am writing 2. In Z also, Z we have three terms, one term, two term, three term. So in bracket, I am writing 3. Okay. So the number of programmable gate will be the maximum number of term into or multiply with the number of output. So maximum number of terms are 3. Out of these 3 expressions, the number of max term is maximum number of max term are in Z. That is 3. So that is 3. That means the maximum number of term is 3. And the number of output X, Y, Z. So we have 3 cross 3, total 9 programmable AND gates are required to design the circuit. Clear? Now we will see the fifth step. Fifth step is to find out number of fixed OR gate, number of fixed OR gate, and that is equals to the number of output. That is fixed here. We have x, y, z as 3 outputs. So we will have 3 number of fixed OR gate. So we have followed all the 5 steps till now. Now we will use these 5 outputs and draw the circuit diagram for it. Okay, so here I'm starting the circuit diagram. Always start the circuit diagram using the buffers, starting from the buffer. So here I'm starting with buffer. I'm drawing for A, then B, and then C. And here one straight line will indicate the normal form of A, and with bubble will indicate the complement form of A. Same thing here, the normal form, and this is the complement form that is coming from the bubble. This is the normal form of C, and if it is coming from the bubble, then it's a complement form of C. Now, as we are having the 9 programmable AND gate, that we have to draw similar to the PLA. So here I am drawing 9 AND gate, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. At the bottom of it, we have to draw the 8 AND gates like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. And as we was doing in PLA, here also you have to extend the line and make the cross line for OR gate. So here I am drawing the cross line to draw the OR gate here. So this is one line, and that will be connected to the OR gate. Here I can say this is X. We was having the 3 OR gates here, right? We calculated the number of OR gate are 3. So here we have to draw the 3 OR gates: 1, 2, and similarly you extend this one for the 3. That will indicate X, Y, and Z. Now the important point, as we was having the maximum number of term is equals to 3. So three AND gates are dedicated for every input now. Okay, three gates are dedicated. 3 gates are dedicated for X. 3 gate will be dedicated for Y. 3 AND gate is dedicated for Z also. So now you see, first we are drawing for X. X is having A bar B. So this is A bar, as this is AND gate is programmable. So A bar B, that you have to draw by cross, and here you write down A bar B. Clear? Now the second term in X is AC. So AC, this is A, and this is C. Here you write down AC. But as I told you, 3 gates are dedicated for X also. 3 AND gates are dedicated for X, but we have only 2 terms. So that extra term you have to add as a fuse. Okay. Here also we are having 2 terms only. The third term will be considered as fuse, because we are multiplying 3 terms, 3 maximum, because here in Z we have 3 terms. So we have dedicated 3 programmable AND gate for every output. Okay. So here we have to include the fuse, because we are having only 2 terms. Here also we have 2 terms. So just to compensate that number of AND gate, we are using the fuse. So here that will be considered as fuse, and here it's drawing it like this: fuse. This is for X. And as OR gate are fixed, that you have to draw by the bubble. It's not a cross, it's a bubble. Okay, this bubble indicates it's a fixed connection for X. So now we got X. Now we will think about Y. Y is having A bar B plus B bar C. So A bar B bar So here we are having A bar, this is B bar, and next one term is B bar C. So next term is B bar C. Here also we will write down this is A bar, B bar, and this is B bar C. And as we are not having any third term, that will be compensated by using fuse. So that we are making it fuse. And as we know that OR gate are fixed here, that will be connected with a bubble like this. And that will be your Y. Similarly, we have to think about the Z. Z having all the three terms, so no need of any fuse. And first term is what? A bar B. So this is A bar. This is A bar. This is B. I'm writing here A bar B. Second term is A bar C. So this is A bar. This is C. You can write down A bar C. The third term here is A B bar C. So this is A. This is B bar, and this is C. A, B bar, C. And this is for Y. So here for this is for Z. So here you have to make the bubble to indicate this is a fixed connection. So this is the only difference between PAL and PLA. In PAL we have a fixed OR gate, whereas in PLA we have a programmable OR gate. And also there is a difference in calculating the number of AND gate.